Okay, so today we will start a new topic on processes, threads, and scheduling. Today's class is going to be somewhat of a recap or a refresher on some undergraduate concepts in processor and thread scheduling. We are going to build it up from that point on, and starting next time, we'll talk about distributed scheduling, multiprocessor scheduling, virtualization, and more advanced topics that are actually part of the course. Okay, so let me, before I start the lecture, start with a computing parable. I relate parables occasionally to just liven up the class. So this one is going to be in two parts. Okay, I'll talk about the first part today, another part next week. So it's about the lion and the rabbit, and it has to do with grad students, as you will see. So the rabbit is the graduate student, and there's a rabbit who is typing away in a forest. And a fox comes along, and the fox says, "What are you working on?" So the rabbit says, "I'm working on a paper titled How Rabbits Eat Foxes." And the fox says, "That's absurd. Everyone knows that rabbits don't eat foxes." So then the rabbit says, "Come with me, I'll show you." And he takes him in the cave, and the rabbit comes out after a while, and the fox does not. And then a little while later, a wolf comes along, and the rabbit is still typing. And then the wolf asks the rabbit, "What are you working on?" And the rabbit says, "I'm working on a paper titled How Rabbits Eat Wolves." And then the wolf says, "That's rubbish. Everyone knows that nothing like that can actually happen." So the rabbit says, "Come, I'll show you," and takes him into a cave. And then after a while, the rabbit comes out and the wolf is disappeared. So then after a while, the rabbit goes in, and inside the cave, there's a lion and a pile of bones. So, so that's the story. And then you can ask, what does this mean? What's the moral of the story? So the moral is basically, if the rabbit is the graduate student and the lion is the advisor, just choose your advisor wisely and you can get away with it. Okay, so next time we will continue this and listen to the next part of the story. So we'll start with a review. Well, actually, I had one thing from last time I did not mention. So we were talking about distributed system architectures last time. And there was one slide I did not cover towards the very end, which was on self-managing system. So we've seen over the last class a whole variety of distributed system architectures, some event-based, middleware-based, client-server, peer-to-peer, and so on. So one that I did not mention, which is autonomous distributed system. Okay, so these are any of these architectures that we talked about. If you also have intelligence in the system, so that the system can make decisions autonomously without human or system administrator intervention, these are referred to as self-managing systems or autonomous distributed systems. And the way they all roughly work is they have three components. So they monitor themselves, so they could monitor the workload or monitor the system state and do some analysis of what they're observing as far as the system is concerned. And based on those observations, you can actually enforce some control. It could be control, theoretic control, or just some other form of control to take some action. And all this loop will continue without any human intervention. So that's basically the intelligence part. And this is often used in many scenarios. If you go and look at cloud computing platforms, they allow you to vary the capacity of your server dynamically based on the workload without any user intervention at all. So if you have a website with, let's say, only one machine, and then the workload on that machine goes up, if the workload exceeds the capacity of the server, the website will go down in the normal case. Okay? If you have a self-managing or an autonomous system, what that web server can do is actually analyze the incoming workload. It can monitor the workload and analyze it. And if it sees that the workload volume is rising and is going to exceed the capacity, or the utilization of the system is going to exceed the capacity, it will take automatic decision, let's say, to start a second server or an I+1 server, which will add to the capacity of the system as a whole and allow it to continue request. So you can vary the capacity of your system dynamically based on workload. Workload goes up, the capacity is increased, so you don't have to turn away requests saying server is overloaded and things like that. So that's a popular scenario where autonomous systems like these are used. There will be others that we will look at as we go along. Okay, so that was the very last architecture that we had wanted to discuss last time. So with that, we will switch gears, come to processes, threads, scheduling, virtualization, and so on. So today's chapter lecture, as I said, is actually going to start mostly as a review of some undergraduate concepts, and then we will build it from there. Okay. So you probably all know what a process is. Okay. So I'm assuming that we don't need to discuss. So we'll distinguish between multi-programming and multi-processing. Okay. Multi-programming essentially says that your OS kernel is able to handle multiple processes that are executing concurrently in the system. Okay? And it can schedule these processes so that they can all make progress. Okay? So you can have multi-programming even on a single core system. Okay? You can have multiple processes running, and you have your CPU scheduler will cycle through the processes or give each process some CPU time so that they can all make progress. Okay, multi-processing, on the other hand, generalizes this by adding more than one processor or core to the system. Okay? Even in this case, you will have multiple processes, and these processes will be scheduled on the different processors, and you will have real parallelism. Okay? If you have two processes running on two different cores or processors, they are actually running in parallel. In multi-programming, you may have concurrency, which means that you will have processes making progress, but if there's only one core, you will not have any real parallelism. Okay, you will basically have to schedule them one after another in some shape or form. Okay, so that's the distinction between multi-programming and multi-processing. Okay. The kernel is responsible for scheduling processes or tasks or even threads for that matter, using whatever resources it has. Okay? And it would have to maintain several data structures. Okay? The kernel has to be aware of what processes are running, what they are doing, how much memory has been allocated, and so on. So the kernel data structure that's used for this is called the PCB, process control block. Okay? Each process is assumed to have an address space. Okay? I'll show you some examples in a picture in just a minute. So the address space contains all of the memory state of that process. Okay? Typically, a process has multiple segments. The code or the text segment is actually the binary instructions of the process. Okay? You will have a stack segment and a heap segment which will store data. Okay? Heap segment is dynamically allocated variables. Anything you malloc or do new or run constructors on the fly is put in the heap. Okay? The stack segments are all variables that are actually local to a function or a method that's being executed. Okay? So processes have segments, they have variables, and they contain code. And typically the way a process executes is to a sequence of transitions. So I'll just draw a picture which we'll look at in some detail in the undergrad class. So the transitions are fairly straightforward. So So that's a state transition diagram or a finite state automaton that captures the transitions a process makes. Very straightforward. You always start in, when a new process starts up, it starts up in new. This is when all of its data structures are being set up in the kernel, when the process is being loaded from disk. Once that is done, it goes to the ready state. The ready state essentially tells the CPU scheduler that the process is ready to execute but it's not yet executing. Okay? CPU scheduler will eventually choose this process for execution. It will be given a core. Okay? At that point, it starts running. This is when it's actually executing. Okay? While it is running, if it does any I/O, okay, it will block. Okay? Because we assume that I/O instructions require you to make a system call transition to kernel and now the kernel executed. So basically, if you do I/O, you will go into a wait or an I/O state and wait for the I/O to finish. Okay, once the I/O finishes, you will go back to the ready state and wait for your turn again. Okay? So you'll cycle through this process. Now, if you are a CPU bound process, you may not do any I/O. So you will run for as long as the CPU scheduler allows you to run. If the CPU scheduler is preemptive, it will use time slices. Okay, so each you will be given a certain amount of time slice. You run. If your time slice expires, you have to give up the CPU for some other process to run. In that case, you'll simply go from run to ready and wait for your next time slice. Okay, so you'll either transition from run to wait to ready, or you'll transition from run to ready. So you'll keep executing in this fashion until the code is done and we basically go to terminate state. Okay, very straightforward state transition picture that captures how processes execute. Okay, so keep that in mind. Okay, so the CPU scheduler is going to look at all the processes or threads that are in the ready state and pick one for execution. That's the job of the CPU scheduler. Okay, so and we'll look at CPU scheduling in just a moment. So those are the processor or process state transitions. Okay. Now there are many different scheduling algorithms, policies that you can use to decide which of the many processes that are in this ready state get to execute next. Okay. Every time, let's say, time slice expires, who gets to run next? Okay. So those are examples of preemptive schedulers. You can also have non-preemptive schedulers which simply schedule a process and let it run until it finishes. Okay. Or it basically gives up the CPU itself by going into wait state. Okay, so we are not going to worry about non-preemptive because most schedulers will use time slices and are preemptive. Okay, so here are some policies that you can use. Round robin, okay, very straightforward. You basically assume there's a queue of processes that are ready. Okay, any process that's in the ready state is in this queue. So you are going to cycle through them in a round robin fashion. You take the first one, give it certain time slice. Time slice expires, it goes to the end of the queue and you just cycle. Okay. Very straightforward policy. Okay. Shortest job first basically says you look at the ready queue, pick the shortest job, the shortest process that you have, and then execute it next. Okay. This policy you can show is optimal in terms of waiting time, okay, but it is not a practical policy to implement. Anyone remember why? So shortest job first essentially says you need to know the length of your process or the job. And that's how you're going to pick the shortest job. If you knew that length, you could of course implement this policy. But if you think about any general purpose operating system, you start a browser, how does the OS know what is the amount of time it's going to execute before it finishes? Yeah, that's up to the user. User may continue using it for a long time or not. So for any process, you cannot actually predict, you cannot estimate this job. You could of course try to guess and predict and use that guess, but that's only going to be a guess. So typically OS kernels don't have the knowledge of length of the job. They only know what the processes are doing now. They don't know what's going to happen in the future. Okay? So it's an optimal policy in terms of the waiting time of jobs. If you can prove that it's optimal, no technique can do better, but it's not a feasible one to implement in practice. Okay. FIFO is very straightforward. First come first serve, so we'll skip that. Okay. Lottery scheduling is a randomized algorithm. Okay. So what happens in lottery scheduling is each job that's in the ready queue, okay, is given some number of lottery tickets. Okay. The number of tickets will determine how much CPU time you will get, and you'll see how that is done. So what happens is whenever the CPU scheduler runs, it looks at all the processes in the ready queue. Okay. It takes all of the lottery tickets, and it runs a lottery. Okay. Think of it as you take all the tickets, you put it in a hat, and you pick one. Okay. The process that holds that winning ticket gets to run next. Okay. So it's purely random because you will use a randomized technique to pick a winning ticket. Okay, so which process gets to go next is randomly determined by who gets to win, who wins the lottery each time. Okay. So now you can control how much tickets each process is given. That's up to the user. And by controlling that, you can control how much CPU time you get, what fraction of the CPU you will get. Okay, so let's assume there are only two processes, and each of them is, let's say, given 10 tickets. So then you have 20 tickets every time the lottery is run. The probability that some process wins the lottery is half. Yeah, so each process gets half of the CPU. Yeah, half of the time slices go to process A, the other half goes to B. Okay, if you give one process one ticket and the other process two tickets, then they'll get CPU time in the ratio 1:2, which means that the first one will get a third, second one will get a 2/3. Okay, because this is going to win the lottery. It has twice as many lottery tickets. Okay, so over some period of time, you will get twice as many time slices. Yeah, over some long periods of time, because it's probabilistic, you will approach that fraction. Okay, so you can control the number of tickets you give to a process and thereby control how much CPU time that process is going to get. Okay, that's lottery scheduling. EDF stands for earliest deadline first. It is a real-time scheduling algorithm. Okay? So what does that mean? There are sometimes there will be processes that need real-time service, that have timeliness constraint, that they need to execute a certain task by a certain time. Otherwise, there's going to be a problem in terms of either the correctness of the application or the user perceived performance. Okay? So in this case, when a process is ready to run, it also has a deadline associated with it, which says that you can run the process any way you want, but you need to try to make sure the process gets at least the next time slot before this deadline D. Okay? If you miss the deadline, then the process is going to have problems executing. What earliest deadline first simply says is you look at the ready queue, look at all the deadlines of the processes that are in the ready queue and simply pick the one that is the earliest. Okay, the deadline that's going to come up next, and you basically schedule them in deadline order. Okay? It's a very popular technique used in real-time kernels. Okay, most operating systems that you see that are general purpose are not designed for real-time use, but there are a whole class of operating system kernels that are designed to ensure real-time performance. Okay? And there are many different scenarios where you may need real-time. Okay? Think of mission-critical applications like control of an airplane or control of actuators in a nuclear reactor. Okay? You want to do things very precisely by certain time. Okay? Otherwise, you may have catastrophic consequences. Okay? Those are scenarios where tasks need to run by certain times in order to ensure that the correctness of the system is not compromised. So tasks are actually given deadlines when they run, and then the scheduler will ensure that they run by the deadline. Okay? Using EDF. Okay, the closest example you can think of that has timeliness constraints in general purpose operating system is media playback, audio and video playback. Okay. So if you think about how video is played out, typically what happens is in a video file, you have video file consists of a sequence of images, okay, and you play them out at a certain rate. Each image is slightly different from the first, so when you just display them one after another, you get the illusion of that things are moving and so on. Okay. So there's something called a frame rate for a video. It basically says you may have, let's say, 24 frames per second. So you need to display 24 images every second. Okay? Or you may have 30 frames a second. That's standard for many video. So 30 frames says every 33 milliseconds you need to display the next image. Okay? If you just take a longer time to display it, the user will see a playback glitch. The video will seem to freeze for a little bit and then it will continue. Okay, that's not desirable from video playback performance standpoint. Okay, so that would be thought of as a timeliness constraint where each frame is decoded and displayed every 33 milliseconds. Okay, so that's an example of real-time scheduling. Clearly, you can schedule these tasks without enforcing this real-time performance. So long as the load on your system is not high, you still see good performance. That's how general purpose operating systems still make those tasks work. Okay. That's a quick run through of processor scheduling algorithms, the uniprocessor world. Yeah, we'll talk about more advanced ones. Are there any questions on this? Okay. So the choice of a particular technique depends on what you are trying to achieve. Okay. I mean, what is the system trying to achieve? There are different criteria. Okay. You may want to maximize throughput. Throughput is the number of jobs that or processes that finish per unit time. You may want to maximize the CPU utilization of in your machine. You may want to minimize the turnaround time or minimize response time seen by users or provide fairness. Okay? At some level, all of these seem like worthy goals to achieve. You would say, why would you not want to be fair, or why would you not want to maximize throughput? So it so turns out that there is no one scheduling algorithm that's going to optimize them all. It's always going to be a trade-off. If you pick an algorithm that optimizes a certain metric, it's always going to be at the expense of some other metric. So you have to decide what is important in your system and pick the scheduling policy appropriately. If you have interactive usage, which means that you have things like laptops where users are actively interacting with the machine, you want to provide good interactive performance, which means you will want to optimize response times. Okay. If you have batch usage, which means it's a server where users submit batch jobs like simulations and then just let them run through completion, you want to then interact, there's no interactive use in that scenario. You want to maximize throughput as the number of jobs that are finishing per unit time, you want to maximize that. Right? You can use a different policy to do the first and the second. So depending on what the use cases are, what a usage scenario is for a particular type of machine, you can pick different scheduling policies. And we'll look at more detail later. This is just a high-level description. So with that background, I'm going to talk about two more policies in a little more detail. Okay, to understand those policies, I'm going to say a little bit about process behavior. Okay, there's some math here which I will not go into a whole lot of detail, but try to provide the intuition. Okay. So to decide how to schedule processes, first we need to understand how they behave. Okay, how do you characterize a particular process? Okay, so there are, roughly speaking, two kinds of processes. A process could be CPU bound, which means it uses the CPU a lot, or it could be IO bound, which means it does a lot of IO. Okay, so typically a process will be one or the other, or over its lifetime it could have phases where it's doing a lot of computation, then maybe it's writing some of its output, so it starts doing some IO, then it goes back to being CPU bound. But at any given time, it will be either CPU bound or IO bound. Okay? And then basically, if you look at how much CPU time you take for what is referred to as a burst, which is a set of computations you do before you end up doing IO, you will see this behavior typically if you empirically look at your processes, which says that most CPU bursts are small, but there are some jobs that are CPU bound that take a long time to finish. Okay. So that's basically the empirically observed behavior in most general purpose operating systems. And what you can do is you can take that behavior and model it as a hyper exponential distribution. The picture, this is the math for it, but that's the picture here, which says that it is essentially somewhat heavy tail. And there will be some jobs that will be very long running. There are lots of jobs that will have small CPU bursts, and then they'll go back to doing IO, or they'll simply finish. Like you type a small command, it just takes a little bit of time, it's done. And that's a small job. Or you have a job that does a little bit of computation and then starts doing IO. But there'll be some long running job that just run for a long time, take a lot of CPU. So that's basically the behavior of processes on most systems. Okay, so you'll have a mix of IO and CPU bound jobs, and CPU bound job needs a lot of CPU time. Okay, with that background, let's take a look at two different scheduling policies. Okay. The first one is simply a priority based policy. Okay. Here you have multiple queues and you assign a priority level to each process. Okay. And you simply do priority scheduling. Higher priority process get to go first, basically are chosen first for execution. So there are many different reasons why you may want to use priority. Okay, so for example, you could take all the processes in your system and say these are kernel processes or these are user processes. Kernel processes are anything daemons, the actual kernel or any other process that the OS is running in the system. User processes are applications users have started. You could give higher priority to kernel processes because they need to manage the system, or user processes. That's the simplest example. Okay? There are many other ways to distinguish them. For example, if you have a mix of real-time and user tasks, you may give higher priority to real-time tasks, because if they miss the deadline, if some user non-real-time tasks takes up a time slice and causes a real-time task to miss his deadline, that's bad for the real-time task. For a non-real-time task, you could have scheduled it a little later. That's not going to impact correctness. You may just see it slow down a little bit. So you may want to give priority to real-time or user tasks and so on. Okay, so priority scheduling is used in many of these contexts. Okay. Now, ignoring that there is priority, let's just take the pool of user level tasks and see how do you schedule those. Yes. So those are also scheduled using a scheduler that uses multiple queues, and it's referred, the common policy that is used is referred to as multi-level feedback queue or MLFQ. Okay, again, something that we do cover in an undergrad course, but I'm going to quickly review it here. So what happens in a MLFQ very simply is there are multiple ready queues, and let's say there is one CPU. Okay. So not one queue but multiple queues. So each queue has a priority level associated with it. Okay. So this is, let's say this is the highest priority, priority 2, priority 3 and so on. Okay. So what multi-level feedback queue does is it basically is a combination of a priority scheduler and a round robin scheduler. It takes, whenever the CPU scheduler runs and says which process should be scheduled next on the CPU, you just look at the highest priority queue. So is there a task in there? If it is non-empty, you simply take the first job there and you schedule it. Okay? So you'll do round robin on the highest priority queue until that queue becomes empty. If that queue, so when you run the scheduler, if that queue is empty, you go to the next highest priority queue. That's non-empty, you'll do round robin there. So at each scheduling time step, you will pick the highest priority non-empty queue and you will try to do round robin on that queue. Okay. That is what the multi-level feedback queue does. Okay. So it's a priority scheduler that does round robin across queues. Now you could ask, what does this achieve? Okay. I think that to answer that, you have to understand how tasks are assigned to different queues. So what the scheduler is simply doing is assuming a certain assignment of tasks to queues. It's doing priority scheduling and round robin. Okay. Now so you have to say the way we are going to assign tasks to queues depends on what we are trying to achieve in the system. Okay. So we said that you can have two types of tasks, IO bound tasks and CPU bound tasks. So before rather than thinking about priority queues and so on, let's ask the question, how should we treat these tasks? In terms of, should we treat them equally? Okay. Should we give priority to IO bound tasks? Should we give priority to CPU bound tasks? Okay. What should we do and why? Anyone have any guesses?
Probably a priority CPU bound tasks. IO bound tasks are probably blocking a lot of them.
Okay, so priority to CPU bound tasks because IO bound tasks will block. That's one thing you could do. Any other thoughts?
Priority to interactive tasks.
Priority to interactive tasks. Okay, so what would interactive tasks be in the system? Because we only know whether they're CPU bound or IO bound at this point. But we don't have a third class called interactive.
So if you're able to distinguish what kind of IO the process is waiting on, then you would probably know if it's interactive or if it's like a disk-based IO. Then we could differentiate.
Okay, so you want to give priority to interactive tasks. Anyone have any other? Any thoughts? No, nobody remembers undergraduate MLFQ. Okay, so rather than saying which kind of job to favor, I'm going to go back to shortest job first. Okay, so remember I said shortest job first is an optimal policy. It always picks short jobs or long jobs and gets optimal wait times. Okay, but it's impractical to implement in practice. Okay. Now if you think about shortest job first, and best analogy is you're driving on a highway. Okay, if you get stuck behind an 18-wheeler, okay, you are going to slow down and there'll be a long line of small cars behind the 18-wheeler that are just following the slow down. But if you could give priority to this car, they will actually go ahead and then everyone makes faster progress. So in this case, what we are saying is smaller vehicles, if they are given priority and don't get stuck behind bigger vehicles, you will actually have better flow of traffic. Same kind of analogy is true why short jobs. If you have a long job running and it's just hogging the CPU, and then there are many short jobs waiting, they will all end up waiting for longer time. But if you let these short jobs go, they will quickly finish. Okay, they will be just out of the system, and then you can run this long job without hurting the performance of other jobs. This is why shortest job first gives better wait times. Yeah, but as I said, you can't actually implement it because you don't know which jobs are long and which jobs are short. You can't predict the future. Okay. Now, what I'm going to, so with that intuition, we can basically go back to this discussion of CPU bound and IO bound tasks. Okay. So I'm going to claim that IO bound tasks are inherently short jobs. Okay. Because they are going to do a little bit of computation and go back to doing IO. They mostly do IO. They do very little computation. Right? So they are going to spend most of their time doing IO, and whenever they need to run, they are going to take, for most practical purposes, they'll take a little bit of CPU time and go back to doing IO. CPU bound jobs are the opposite. They are like long jobs. They just sit on the CPU. You let them run, they'll run for long periods of time. Okay? So if you wanted to approximate what shortest job first did, okay, but do it using the distinction of whether you are an IO bound or CPU bound job, what would you do now?
Well, so if it's cut into time slots, we can assume that it's CPU bound if it never actually blocks during if it completes the time, and if it has to go do an IO halfway through, we assume it's IO bound.
Okay, so you are explaining how we distinguish between the two, right? So that's true, and we'll come to that in just 1 second. I was simply asking you, based on what I just said, what would you give priority to? Yeah, so you should say you should give priority to IO bound, because I just argued that IO bound jobs are small. Shortest job first gives priority to small jobs and does well for everyone. So here we should basically give priority to CPU bound. Yeah, so now what we are saying is we will not treat all jobs equally. We will prioritize and give IO bound jobs higher priority, CPU bound jobs lower priority. Yeah, and then we can approximate what SJF did. Then you should say, although now this does not require you to know job length, it just requires you to know process type, is it IO bound or CPU bound. So you should then ask, how will you tell whether a job is IO bound or CPU bound? Okay, when a job starts up, it doesn't declare itself, I'm going to do a lot of IO. Neither does it tell you the job length. So if you wanted to give priority, what would we do?
Over a period of time, you measure how much CPU time a process has taken. If it's taken more time, then it's CPU bound. If it's taken less, or a longer period of time.
Okay. So I'll just generalize what was just said. You can tell whether a job is CPU bound or IO bound by observing what it is doing. You may not know the job length. That's what is going to happen in the future. But you can observe what a job is doing presently. Is it doing any IO or not? And that you can use to estimate whether you're IO bound or CPU bound. Okay, so this is going to approximate what shortest job first did by simply observing the current behavior and assuming that the near future is going to look like what the current shows. Okay, so this is how the policy works very simply. Okay, so you start when a new process comes in, it joins the highest priority. Okay, so basically, whenever you execute since you're going to do prioritized scheduling, you pick a job from the front here and you run it on the CPU. And then you observe what did it do during the time slice. If it ran through the whole time slice without doing any IO, you label it as temporarily CPU bound. If it blocked in the middle of its time slice and started doing IO, that's the same suggestion that was actually just a few minutes ago. So you say it's CPU IO bound because it just did IO. Okay? So if your CPU bound, you used up your entire time slot, did not block, you are going to be dropped in priority. Because we want to basically give CPU bound job lower priority. Okay. On the other hand, whenever a job runs and it blocks in the middle, you are going to say that's IO bound, it will rise in priority. You move it to the higher priority. Okay, that's what the policy is going to do. Okay, it will basically observe what the job did. If it runs through its time slice, you join the next lower queue until you reach the bottom. If you anytime you actually block in the middle of the time slice, you start rising. Okay? So what this will do is over time, IO CPU bound jobs will drop and will end up in the lowest priority queue. IO bound jobs will rise and stay in the highest priority queue. And this will happen automatically. You don't need the jobs to tell you whether you are CPU bound or IO bound. Okay? And since you are doing prioritized scheduling, you will basically favor IO bound jobs before you do CPU bound jobs. The last point I did not mention is as you go down, you can also increase the length of the time slice. Okay, because you know that your CPU bound jobs at the bottom. So give them larger time slice. If there are no IO bound higher priority jobs waiting, let them run for longer. Why switch them out and incur context switch over? You basically amortize your context switch over. So time slices increase as you go down. Priority decreases as you go down. Okay, so that's MLF. Yes, question.
So, what is the default time slice that you use for observing whether it's an IO or a CPU?
Okay. What's the default time slice? So that basically for each queue you are going to give a time slice. Okay, that's up to how we configure it. So you can say that's a 10 millisecond time slice, that's 20, that's 40. So you increase it exponentially. Okay. So whenever a job is taken from a queue and run on the CPU, it will get the time slice associated with its queue. And you simply observe what it did in that time slice. If it's blocked, then you are IO bound. If it didn't, you will drop. Okay. Alright, I think I spent a little more time on this, but hopefully it's clear what MLFQ does. So with that, we are going to switch gears a little bit, talk about processes and threads. I'm going to introduce threads more formally. Okay, so you probably know what a process is. The definition is here. The traditional process is basically one address space and a single flow of execution or control through that address space. Okay, in other words, a process is also referred to as a single threaded process. It has one thread of execution. Okay. You can generalize this concept and have multiple threads of execution through the same process, and then you get basically what is referred to as a multi-threaded process. Okay, and so you have a flow of control through the address space, and you can have concurrent flows, and all of these threads will actually share that address space. And here is a picture of what is a multi-threaded process. So this is your process address space. This is how the process is laid out in memory. These could be segments, code segments, and so on. So what you have is literally multiple things executing, threads executing concurrently through this address space. Like one thread could be executing function foo, another thread is executing some other part of that code. Right? Each gets its own program counter, register, and its own stack. Okay? So here you have thread 1 executing this part of the process, thread 2 executing that part of the process, thread 3 executing some other part. You can have as many threads as you want depending on the application. Okay? Single address space. Okay? So they are all shared by the threads. So what that means is each of them gets their own stack, but global variables are all shared. Okay? So one thread can access a global variable just as or any data structure that's global like another thread. Okay? So everything within the address space is actually shared in terms of data and variables and so on. Okay? So that's basically what threads are. Okay? So they are basically flows of control through an address space, and each thread is going to get its own program counter, own set of registers, own stack. So you can write, rather than using a single threaded process, you can write multi-threaded processes where different threads are responsible for different tasks. And I'll show some examples of how to do that in just a moment. Not how to do it, rather how some applications do it. Can I clarify any questions here before we go on? Yes, I'm going to show. So you will see if you actually look at most applications, right, that they are multi-threaded. I'm going to show an example of processes running here. Okay, so this is just simply a list of all the processes running on this machine. Here is the number of threads associated with each process. So you will see that this Google Chrome, it's a browser, it has 29 threads running in it. Okay, so there are 29 threads of control executing on the different parts of that process. Okay, here is Keynote, that's the presentation application, there are 15 threads running through. Okay. So you will have, so most processes you will see are multi-threaded because they have partitioned the process code into threads, and threads are doing things concurrently. Okay, so, and we'll come back to the browser example in just a moment. Okay, so why use threads? So if you have large multiprocessor systems or multi-core system, this allows you to get true parallelism for your single application. Your application is partitioned into threads. Threads could run in parallel on multiple cores, so your application is actually running in parallel. Okay, if you are single-threaded process, then you will not get real parallelism for that process. That process can execute on one core at any given time. Some other processes could execute on the other core. Okay, so you will get parallelism across processes, but not within a process. Okay, multi-threading allows you to get real parallelism within a process in the scenario where you have multiple processors or cores. Okay, that's one reason to do it. Okay, also, using threads allows you to reduce the context switch overheads that are incurred by the kernel. It is much cheaper to switch between threads than to switch between processes. Okay. And the reason is whenever you run the CPU scheduler and do a context switch, what that CPU scheduler has to do is it has to take the state of the process and save it somewhere. Because when you resume execution, you resume execution exactly where you left off. So what that means is you take all the registers and you save them into a kernel data structure. Okay. And then when the new process runs, you will take its registers that were saved and load them. So then it can resume executing wherever it left off. So you have to do this bookkeeping of saving its state, not just the register, the page tables, all of the associated state of the process has to be stored somewhere, so that when you execute it later, you can reload that state. So it starts off from where it left off. Okay. That's all context switching. Okay. So when you do a switch between process, you have to take all of the process state, save it, because you may start executing a new process and load its process state. But when you're switching between threads, okay, the address space has not changed. So you don't have to change page tables or anything like that. Okay. All you have to do is save the state of the registers and load the state of new registers. But page tables, all of that are the same because it's the same process. Okay. So less information has to be saved and restored. So it's faster. Okay. So context switching between processes is slower than context switching between threads. So having multi-threading within a process allows you to reduce this overheads that the kernel will see. Okay? Same is true of thread creation, thread deletion. Creating a process is far more heavyweight than creating a thread, because the address space for a thread is already there. You're simply creating one more thread in that address space. Creating a new process involves loading a new process into memory, and a lot more work has to be done by the kernel. So those are some advantages of using threads, and whenever you have multi-core systems, you do use multi-threading extensively. Okay. So here is another way to look at this, what threading buys you. So we start with a traditional process, which is a single-threaded process. Okay. A single-threaded process basically has no parallelism. There's only one thread of control. Furthermore, it's blocking. Okay. If that process does I/O, the entire process blocks. And nothing can happen in that process until that I/O finishes. That's the state transitions I showed you. I said if you are in ready state or run state and you do I/O, the whole process is blocked. It waits until the I/O finishes. Okay. Now let's take the other extreme, which is this process has multiple threads. Okay. I've already said that you will get real parallelism, which you could not have gotten in the single-threaded case. You have two threads of the process, run it on two cores. Now your application is actually getting twice as much CPU time. Okay. That's furthermore, it's real parallelism because it's actually running in parallel. Okay. And what you can do is, because you have the presence of threads, okay, the threads can still do I/O, like you did in the single-threaded or the traditional process case. But when a thread does I/O, okay, only that thread of that process can block. The other threads can still continue to run. Okay, so the process as a whole can continue to execute, but only the threads that have actually issued the I/O instructions are blocked because they have to wait for their I/O to finish. So this will also give you more benefits that you could not have gotten in the single-threaded case. Any questions on this?
So is it always good to use threads?
Okay, so that's a good question. So question is always used to good to use threads. We will come back to the process versus thread discussion when we discuss the web server architecture, and we'll ask that question for web server: what is the most efficient? Okay, in terms of many different dimensions, and we'll examine that. But I'll answer that question in a slightly different way here because I did not mention the middle alternative. Okay? So if you let's say you had a system that did not support threads at all, right? Only supported single threaded processes or traditional processes. So if you just do it the usual way, there is no parallelism at all. Basically, you have to execute one and one thing only, and then whenever you block, you are going to go off and do I. Okay? But there's one way to emulate parallelism in single-threaded processes. Okay? And the way you do that is you basically use what is referred to as an event-based design for your system, okay? Which uses non-blocking calls. To make all the calls non-blocking, I/O non-blocking, and you use event-based system, then you can make your process have some parallelism in it. Okay? Event-based design is very popular whenever you have GUI applications. All GUI applications are written as event-based. Okay? You click on a button. Let's say you have GUI, you click on some button, and then what happens as a result of that is you go into the event handler for that button and you execute that code. You click on something else, you basically go into the event handler for that event and you execute something. Okay, so that's basically at a very high level what event-based applications mean. Okay. Now the important thing is not only do you want event-based, you also want non-blocking. Okay. If you use non-blocking I/O, what that essentially means is your process issues I/O instructions, okay, but it does not block, it does not wait for the I/O to finish. Okay. It simply hands off the I/O request to the kernel and says interrupt me later when the I/O finishes. Okay? And the process continues executing. Okay? So now it can basically say this I/O is outstanding, so let's do something else. Okay? Something else could mean you issue an I/O request, but user clicked a button somewhere. You go execute that event handler, so you can continue to make progress. Later on, when the I/O finishes, there will be an interrupt. Then you will jump into the interrupt handler, which is exactly an event, and then you will process the I/O. So you can take a blocking process, which is here, and make it all non-blocking and event-based. In this case, you get parallelism because I/O instructions don't block the process. The process can actually do other things while the I/O requests are pending. Okay? So you are sort of not real parallelism in that you're not running on multiple cores, but you have some concurrency. You can do multiple tasks. When one task of the process is issued I/O request, you can continue to execute other tasks using non-blocking calls. Okay? This is a way to write applications. Probably you have not used non-blocking calls before because by default you will use blocking calls. Whether it's a single-threaded or a multi-threaded process, you issue I/O request, you read from a file, you write to a file. Those are all blocking calls. But you have asynchronous or non-blocking versions of all of these I/O methods that you could use to implement these kinds of applications. Okay, we'll come back to when we talk about web servers. Come back to this and talk sometime in the next 2 or 3 classes. Any questions on this? Anybody has written event-based applications? If you've written GUI applications of some shape or form, you have done event-based programming. Although you may not have written all the underlying code, the underlying code that generated for you actually does this. Okay, so now since we are actually talking about benefits of threading, the thing here is threads retain the illusion of a blocking calls and the usual abstractions you are used to in a single threaded process, but give you parallelism. So what has happened is you've taken the process, you partitioned it into threads. Each thread is doing blocking calls. So you can just write your code the way you normally write single-threaded processes, but you get parallelism. Writing event-based code is much more complex. As you can imagine, you have to write event handlers and the code jumps from one location to another in your address space depending on what events have occurred, and so on and so forth. A lot more complicated code to write. Multi-threaded code is a straightforward generalization of writing single-threaded processes once you get the concept of what threads do and how to partition your code into threads. Okay? So from a software engineering perspective, okay, although both of these allow you to extract some parallelism, this type of code, which is multi-threaded processes with blocking calls, is much more easier to write than event-based code, which uses non-blocking code. Okay, so as a result, you will see that when you want to extract some parallelism, this is a lot more common. Okay, that is a lot less common, unless you're doing certain kinds of applications. Okay. All right, so let's now look at a few examples, and then I'll talk about some kernel page and user level threads. First example is web browser, how you can make it multi-threaded. I think you know this. Okay. So if you have a browser application and you want to write, you could simply write it as a single-threaded process, and if you'll quickly realize that that's not very efficient. Okay, so let's say user clicks on a link, okay, on an HTML page. Okay, then the browser has to go establish a connection to the server that corresponds to that HTML or HTML request. Okay, you establish a connection, you send a request, you wait for the response to come back. That will typically be an HTML page. Okay, and you parse the page. If the page has images embedded in it, then you have to go and fetch each image. So for each image, you'll set another connection up, download the image. Okay, and then once images are all downloaded, you will have to display the HTML page and all of the images in there. The browser was a single-threaded process. You would have to do all of this operation one step at a time and wait for all of them to finish before the page is displayed to the user. Okay. That can substantially increase the latency the user sees. Okay. You have clicked on the link and you're waiting, and the browser is going fetching the page, fetching the first image, fetching the second image, all in sequence. Okay. So you basically can see the response time will be the sum of all of those operations. Okay. Now you could make your browser multi-threaded. In this case, you may start getting some benefits and better performance, and here is how you can do this. Okay, so let's say you click on a link. The simplest form of parallelism is click on a link, right? Set up a connection. So you start a thread that sets up a connection to the server and downloads the HTML page that is in the link. Okay? HTML page comes back. So you start another thread and says go parse it and extract all the images that need to be fetched. Maybe there are 10 images in there. Right? Then you can start 10 threads and say each thread go and fetch an image. Okay? So now there are 10 connections in parallel. Okay? They are all downloading the image that has been given to that. Okay, now what you can do is you can start rendering the page as each image is fetched. Okay? Let's say the third image comes back quickly. Okay, you can already display the text and the image can start loading. You don't have to wait for all of them to finish. Okay? So as each image comes back, you can render it and start displaying it. Okay? So you do this and you start seeing better interactive response. The text comes back and images start loading quickly. You don't have to wait for all of those things to have finished, as you would have to if you had implemented your browser as a single threaded process. So you've gotten some benefits of concurrency. Okay. So this is basically some advantages of going from a single threaded to multi-threaded applications. And that is typically what browsers would actually do, what I just said, in some slightly more sophisticated ways. Okay. So that's a client that is multi-threaded. Here's a server that's multi-threaded. Okay. Same kind of considerations hold. Okay. If you had a single-threaded server and lots of requests were coming in, okay, so because if it's a web browser, web server rather, anyone can send a request to the web server saying, give me this such and such page. That's a HTTP request comes in. Okay. If you're single-threaded, you will simply have a queue of outstanding requests. You will take the first request from the queue, go off, fetch the page from disk or whatever, and construct a response and send it off. And then you take the next request from the queue, you do the same thing. Okay. And remember that fetching a file from disk is I/O, it's blocking. Okay. Fundamentally, what that will mean is you take a request that has come in, Okay, you look at what HTML file or JPEG image or whatever has been requested, you go and read that data from file and then you send it over. And while that is being read, the whole process is blocked because that's a blocking call. Nothing else can happen. Okay. You could, of course, make the server multi-threaded. That's the picture that's being shown here. So what happens in a multi-threaded server is you have what is referred to as a dispatcher's thread and a pool of worker threads. Okay. Requests come into the dispatcher threads. So rather than having a queue of outstanding requests, what the dispatcher thread simply does is, it says request came in, is there a worker thread that is idle and waiting for some work? If there's an idle worker thread, you simply give that request to the worker thread and go and process the request. Okay. So now if n requests come in simultaneously and then n worker threads, each request is assigned to a worker thread. And these worker threads can execute in parallel. One worker thread has is retrieving an HTML file from disk. The process as a whole doesn't block. Only that thread blocks. Other threads can continue to issue their own request to fetch data or send back responses. Okay, so the process as a whole can make more progress. The server process if you're multi-threading. Okay, so this is basically a very standard way to write servers where there's a master thread that receives requests and then it hands it off to slave threads that process requests and send back responses. Okay. Now the size of this pool, worker thread pool, will determine how many requests you can handle concurrently. Okay. If you have n threads in the worker pool and n plus 1 requests come in simultaneously, the last request has to wait because all the worker threads are actively doing something. So that request will be queued up, and as soon as the worker thread becomes idle again, once it finishes its request, then you will give it the next request. Okay. So the size of this pool, we'll come back to the Apache architecture in a little bit. We'll see that the size of this pool has some implications on how many requests you can serve, what load you can sustain, and so on and so forth. Any questions on this? Yes.
Why does Apache not just spawn a new thread every time the dispatcher gets something instead of having a pool of worker threads?
Okay, that's a very good point. So I mentioned this architecture where you have a pre-spawned pool of worker threads. Request comes in, you find idle thread and you do. Another very standard way to write servers is what was just mentioned. It's referred to as a thread per request model. Okay? New request comes in, you dynamically create a thread, hand it the request, and go off and execute. Okay, it will execute that request, and once the request is done, the thread terminates itself. Okay? So every time new request comes in, you spawn a new thread. Okay? And the thread will go off in, and then the lifetime of the thread is precisely the time needed to process that request. So this is referred to as a thread per request model. Every request creates a new thread that services that and that request only, and then it finishes. Okay. So the advantage of a thread per request model is it scales graciously with or gradually with the increasing load. As more requests come in, more threads are spawned. Okay, you don't have to wait. Unless in this case, if you have n of these pre-spawned, if n plus 1 requests come in simultaneously, one request has to wait. If you had a thread per request model, if n plus 1 request comes in, n plus 1 threads are created and they all go off and service whatever they were asked to service. Okay. So that's an advantage of a thread per request model. The disadvantage of a thread per request model is if you have a very high volume website, there is a lot of overhead spent in creating and deleting threads. Okay. Creating a thread takes some overhead. Doesn't come for free. Okay, you say thread create or pthread create or thread.create in Java, it has to go set up the data structures for the thread, it has to create a stack for the thread, it has to create its own set of registers and so on. That's going to take some overhead. Okay? And you pay all of that overhead, the thread is going to service a request, maybe it takes a second to service it, and then you throw the thread away saying now finish. So then you have to clean up all of those data structures as well, deallocate the stack, deallocate the register structures that you created and so on. Okay, so basically in a thread per request model, you will spend an overhead of thread creation and thread deletion for every request. Okay? And that can be high. In this case, if you pre-spawned a pool of threads, okay, you pay that once and you basically amortize it over the lifetime of your server until the server is terminated. Okay, so that's much cheaper. You have thrown out the frequent thread creation and thread deletion overheads. Okay. So you have these two choices. Either you can decide how many threads to create on the fly as requests come in, so no request has to wait, but then you pay the price of creating and deleting threads. Or you pay that price once by trying to guess how many worker threads to have. But if you guessed wrong and more requests come in than your worker thread, they're made to wait. Next question.
So if there is a, I mean, if there's only 2 or 3 processes that are running in like 2 or 3 threads and the rest are idle, that will not cause any overhead at all.
Okay.
The idle threads.
Question is, what do idle threads do? The idle threads have consumed resources in that there is some memory state allocated for them. But since they're idle, they are not going to take up any CPU time. They'll just be sitting there waiting for work. So idle threads don't consume CPU time. But if you have too many idle threads, they do consume memory state. So your memory size of the process will be larger than what it needs to be. But you will not use up CPU time. Okay, so you will waste memory but not CPU if you're idling threads. Yes.
I'm assuming you can kind of mix the two models as well and sort of start with like a smaller pool, then if you find out you have too many requests, then just create new threads but don't ever kill them.
Yes. So point that is being made is you can combine the two by pre-spawning a pool and then varying the size of the pool as the load increases or decreases. Okay? In fact, that is exactly what Apache does. It will start with a default, and if it sees that there is a queue of outstanding requests, it will dynamically increase the pool. Okay? And likewise, if you go up and you created lots of threads that are just sitting there idle, okay, rather than wasting their memory state, it will deallocate some of them. So it will always have some spares. So there is the next request can always get immediate service. Okay? But if you have too many spares, it deletes some of them. If you have no spares, it tries to add to the spare. That's basically what it does. We'll come back and discuss that in more detail when we do Apache.
Okay, so web servers, it makes sense to have these pre-spawned set of threads because you know that you are going to get some requests. Is there a counterexample where this strategy won't be, not just in web servers but some other architecture where this pre-spawn pool may not be working to your advantage?
Right. So I think there are only two ways to write a multi-threaded server. You create the threads on the fly, which is the thread per request model, or you use the pre-spawned model. Okay, pre-spawned model is more complicated to write because you have to have a dispatcher that keeps track of what the threads are doing, which ones are idle, which ones are not. You may want to dynamically change the size. All of that is more work. Okay. The simplest servers to write are you say thread per request. Request comes in, create a new thread and let it do what it wants. Okay, that code is significantly less complex to write, and it does well unless you have really high volume traffic. You may want to say I'm willing to pay the price of extra thread creation and deletion. Okay, it doesn't impact me a whole lot. Okay, but if you're really looking for efficiency because you have very high volume request rate, then you may want to say I will go with the extra cost of putting in a pre-spawned pool and then trying to manage that pool to save the cost of thread creation. So it's mostly an efficiency trade-off, okay, and how much code you want to write. Any other questions to this? You have only one process on the server? Is that your question? So the server machine can have other things running on it. Okay, but the assumption is this server process will probably be what is taking most of the resources, but doesn't have to. There's no restriction. Okay, this is just another process in the system. If you have multiple processes, can you assign requests to other processes? Is that what you're asking? You could do that. In fact, there are processes that will do exactly what I said here on a per process basis. They may go so far as to say request came in, let's spawn a new process and hand the request to that process. Okay, or you have a pre-spawned pool of processes. Okay, early versions of Apache were not multi-threaded, they were multi-process. That have pool of spawned processes. So you would actually hand the request from one process to another, to a slave process saying go assign this request to that process and say go service it. Yeah. So you could certainly do that, but you don't necessarily get anything by mixing the two. But if you already have multiple threads, it is much cheaper to actually create a new thread than pay the cost of transferring this request to another process and having that process run. It is much cheaper to say, let's create one more thread in this process. But if you have a pure multi-process model, you can do that. Okay, but there's only one thread in that process, and the process is in that case. Any other questions? Okay, so
Will there a problem arise if because the threads are sharing the same address space only?
will the problem arise if they have shared the heap? The problems arises if there is a bug, right? The problem is if there is some bug and one thread crashes, the whole server will come down. Okay? Same is true in your browser case. Right? So the way I would answer that question by saying, if you look at let's say Firefox's model of building a browser and Chrome's model of building a browser. In Chrome, the tabs that you see, if you have multiple tabs in the browser, they're independent processes. And the reason for that is also security. If you have JavaScript or your Flash player dies, only that tab is going to die. Okay? If you have a single threaded, multi-threaded but single address space, if one tab breaks, the entire browser will crash. So you get isolation. That's about the only advantage. Because the bug can only infect that particular entity rather than entity. In the multi-threaded case, one thread can bring the entire application down. Okay, so I'll go through this very quickly because again, this is somewhat of a recap from how threads work and so on. So I'll talk about three different ways of implementing threading packages in a typical system: user level threading, kernel level threading, and lightweight processes. So we'll start with user level threads. So what user level threads are is a threading support that's implemented purely at a user level without asking for any support from the underlying kernel. Yeah? So the kernel in this case does not know of the presence of threads inside processes. Okay? It sees the process as a single threaded process. There's a threading library that has been associated with a process that creates the manager's threads for that process. Okay? The threading library and the presence of those threads are not visible to the kernel. The kernel simply sees this as a single threaded process. And once it's so scheduling in this case is a two-level decision. The CPU scheduler of the kernel will schedule that process. Once the process is scheduled, the threads library has its own thread scheduler that will pick one of the threads to run whenever the CPU scheduler asks the process to run. There are two levels of decisions. Okay. Advantage of user level threads is it does not need OS level support. So even if you had an OS that did not have native support for threading, you could still write multi-threaded applications on that system. Okay. By implementing, by using a threads library to write your application. Okay. So you may have old kernels or stripped down embedded systems or whatever that don't have native support. Most general purpose operating systems have native support for kernel. But some, if you have a OS for whatever reason doesn't support it, rather than saying I can only write single threaded processes or traditional processes, you can use a threads library to write multi-threaded application. That's the advantage. Okay? The other advantage is you can pick whatever favorite library you want. It may use different scheduling policies, for instance. The threads library has to implement its own scheduler. So you may have three different libraries that have three different scheduling policies. So you say for application A, I like round robin, and this scheduler, the threads library implements round robin, so I'm going to use that threads library. For some other application, I want to do something else, so I'll use something else. Okay? So you have advantage of even choosing a library or that implements the right kind of scheduling support for you and so on. Okay? So those are all advantages of user level threads packages. No kernel support is needed, flexibility in scheduling, and last but not least, it's very efficient because thread creation, thread deletions are simply library calls. They are function calls inside a process. Okay, the library is part of the process. You say create a thread, you go to the library method, it will create a thread for you. No OS involvement is necessary. So it's very cheap to create and delete threads. Okay, so highly efficient. Disadvantages of user level threads is that because the presence of threads is not visible to the kernel, if any thread makes a blocking system call, the entire process will block, even though there may be other threads in the system that are ready to run, because the OS doesn't know about it. It says one IO request coming from the process, it says, okay, this process is doing IO, it blocks the entire process. It doesn't know there are other threads, it can't tell, so it can't let those other threads make progress. Okay. So one thread can block the entire process, just as a single traditional process. You do IO, the whole process blocks. The same is true here. Okay. So basically, if you make traditional blocking system calls, everything. You can of course use asynchronous IO and get around that problem, but that will complicate your code. So traditional IO calls will cause the system to block. Okay. The other big disadvantage is you don't get real parallelism. Okay, you may have multiple cores and your user level threads library that implements threading, but you can't take advantage of this other cores because that process looks like a single entity to the kernel. It gets only scheduled on one CPU or one core. Even though there may be 100 threads in it, you can't take one thread and schedule it on core 1 and another thread on core 2 because the OS doesn't know of the presence of threads. It can't allocate 2 cores to that process. It thinks of it as a single threaded process. Okay, because the OS is not involved in the thread management at all. So it doesn't even know. Yes.
How does the OS handle the asynchronous IO?
How does the OS handle asynchronous IO? Typically, when you issue an asynchronous IO request, it's like a typical file read or file write, but it tells the kernel saying, don't wait until the data has been read or written. Return immediately, and then send an interrupt when it's done. That's the semantics of the call. The system call semantics are different. Okay, typically, if you do read, which is a system call, or you issue a read at a library level, it triggers a system call. The call will wait until the results are available. The call will return. That's blocking. Okay, in a non-blocking, you will basically hand it, the call will return immediately. So you will basically the function or whatever will return, but the request hasn't finished. So you have to wait for a later time to get the results. Okay. Kernel level threads. This is just a picture that shows user level threads. So these are your processes. That's the library that manages threads. And you will see this is what the kernel actually sees. Okay, so it sees this entire process as a single thread. Okay, because it doesn't know of the presence of multiple threads. As a result, each of these processes can be only mapped onto one processor at a time. So you don't get real parallelism. Okay. So kernel level threads are everything that is a disadvantage and the user level thread becomes advantage. Everything that's an advantage becomes a disadvantage. Okay, so it's all flipped. So kernel level threads are thread packages that kernel provides native support for. Okay, the OS is supporting threads for. Okay. OS knows about the presence of threads inside a process. OS can exploit the presence of threads inside a process. So if there are 2 threads, here is an example, there are 2 threads, or if there are 3 here, okay, 3 threads, the kernel knows about the presence of all of those 3 threads inside the kernel. It can actually take 2 of these threads and map them onto 2 processors simultaneously. Okay, so you get real parallelism inside a process. Okay. Furthermore, if this thread does a blocking IO call, only that thread is blocked. This other thread can continue to run, and so can other threads of that process. Okay, so one blocking call doesn't block the whole process, only that thread. Okay. But you are bound by whatever CPU scheduler is actually implemented in the kernel. Like user level thread, you can't pick and choose. You're stuck with what the kernel provides. Okay. Thread management is more expensive than user level threads because when you say thread create, that's a system call. The OS has to be involved. It's not a library call. Okay. System calls are more heavyweight than just calling a function or a library inside a process. Okay. So all the advantages basically become disadvantages and vice versa. Okay. So I'm going to talk about one last thing and then end here. Okay. So there is something in between user level threads and kernel level threads which are referred to as lightweight processes. Okay. A lightweight process is simply a schedulable entity inside the kernel. It is something that a kernel can schedule onto a processor. So when you have lightweight processes, the kernel allows the application designer to decide how their threads map onto lightweight processes. If you have a one-to-one mapping for every thread inside the process, you actually create a lightweight process and map it onto that process. You get the same thing as kernel level. So here you will see in this previous picture that each thread here was mapped onto something there, which was simply the thread itself. So in this case, you will have a lightweight process and a one-to-one mapping. Okay, in that case, you basically get the same benefits of kernel level. Okay? But you could say I want only one lightweight process for the entire real process and take all of its threads and map onto one lightweight process. That will look exactly the same as a user level thread. In user level thread, you end threads that mapped onto something that the kernel was aware of. Okay, and you can get anything in between. You decide which subsets of threads map onto which lightweight processes as the application designer to get whatever scheduling properties you want from the system. So what would happen is you create some lightweight processes, you create some threads, and the application designer decides what mapping they want at runtime, and they will get appropriate behavior. You could pick one-to-one, looks like a kernel level thread system. You get many-to-one, you get a user level thread. You can get many-to-many. So that will look something in between. Okay, some threads map onto one lightweight process, but some other threads get their own lightweight process. You can do whatever you want. Okay. So it gives you anything between the two. So in that case, you are not stuck by whether you are doing user level threads or kernel level threads. You basically can achieve anything in between. Okay. So some operating systems like Sun's operating system, which known as Oracle's Solaris, implement lightweight processes. Okay. Most OS kernels just simply do kernel level threads. Solaris goes one step further, saying here is an extra layer of flexibility for users. You decide how you want the kernel to treat your threads. Okay, so you can pick any flexible policy you want. Okay, so I'm going to end it here, and then we'll continue the discussion next time.